So today we are going to focus on this ADA Boost training. Okay. After this is kind of second step because the first one is about feature calculation. So last class we studied about highlight features, and especially as we have already discussed, highlight feature is kind of traditional feature. Okay. But in this paper, they propose a special image representation called as integral image to calculate the highlight feature, much faster. Okay. So now, do you all understand about how to calculate the integral image and how to use it? Is that clear now? Okay. Yeah. So then now let's continue with AWS training, and I think we can finish this algorithm today. And the next step, the final step is, the cascaded classifier. So we'll study about cascaded process, next class. Okay. Yeah. Okay. So then let me ask you a question. If you remember from last class, what is the main purpose of AWS, training in this algorithm? What is the core and main purpose? Okay. Detecting objects, it is kind of, global, target, okay, global purpose of the whole, algorithm, okay. But this, specifically, this one, ADA Boost training in this, face detection system, the main purpose as Raul answered, purpose of this one is, feature selection, okay. So don't remember the fact, what we want to do through this, ADA Boost, especially ADA Boost training here is selecting good features among many features. Okay, so here the many means, over 180,000. So this number is kind of combination of all different types of highlight features with different positions, different size, and different type. Is it clear? Okay. So we are starting. So from our previous step, calculating, preparing the highlight features. So now we have all possible over 180,000 features. Okay, it is ready now. We are assuming they are ready at this stage. Okay. By the way, this number of features, it is too big. Okay, too many features. So it is actually practically impossible to use all of them. And it is not, desirable to use all of them. So we have to select some good features among these 180,000. Okay, that is the purpose of this algorithm, this learning algorithm. Okay, so again, the feature set is now ready, very huge, feature set. And training set, the training set means the training image, training samples. It is, composed of positive and negative samples. So here positive means phase, negative means, non-phase samples. Okay. Then using through this, learning process, what we want to do is to select good features, and in other words, every feature is actually corresponding to one weak classifier. So finally, if we select good features, it means we are generating weak classifiers. Okay, yeah. So let's actually, the concept of weak classifier, weak learner, weak classifier is new for now. So we'll discuss about it detail later. Okay, today. Okay, yeah. So anyway, so let's the purpose is to find the good features, and finally from the selected good features we can generate weak classifiers, and finally we want to make one big and final strong classifier. Okay, so that is the target of this AWS algorithm. Okay, let's move. So do you remember this concept of good feature and bad feature? Okay, so this is very conceptual, example, right? It's not the real case. So as we have already discussed yesterday, so this black graph means, bad features. Okay, so with this kind of feature space, when you look at the distribution of positive and negative samples in this feature space, F3 and F4, it is almost impossible to draw any line, okay, whether it is linear or non-linear, okay. So it is almost impossible because they are all mixed, the positive and negative. So it looks like it is almost impossible to make a good line to distinguish the positive and negative, right? But in the blue graph, the feature F1 and F2, it looks like, it is much easier to distinguish, the red dots and white dots, right? The positive and negative samples by drawing one simple linear line. Okay, two simple linear lines. Okay, so our target is to find this kind of, good features. Okay, so when we determine good features, or if it is bad features, then it means, how it can classify with a certain, this threshold. So this line here, so this kind of, for example, line, vertical one, horizontal one. Okay, so this line means a kind of threshold value. Okay, so if the feature value of one sample is less than this line, then I want to say it is positive phase. Larger than this line, it is negative. Okay, so this way, one simple way is to define a threshold, calculate a threshold, and make a classifier. Okay, so feature 1, for example, F1, okay, by calculating threshold, this black dotted line, vertical line, then we can make a simple classifier. Okay, we'll see the detail later, the real example later. Okay, but this is the concept of classifier. So this is the relationship between feature and weak classifier. Okay, F2 is just feature, right? The feature value. But if we set this kind of horizontal red line, this is one value, threshold, then it can be a weak classifier, one classifier. Or it can say, oh, this is phase. Larger than this line, this value, this is phase. Oh, smaller than this value, this is non-phase. Okay, so this is kind of binary classification. Okay, so this every feature can constitute every weak classifier by combining with the threshold value. So we'll see how to calculate the threshold value for every feature. Okay, so that is the concept. Okay, so let's see. And by the way, when let's assume we have good features. Okay, so in this case, in this slide, the next slide. Okay, let me go to next. Okay, in this new slide, slide number 18. So the left top corner, we have three feature spaces. Okay, and 3 different, threshold kind of line, classification, line. Okay, so every graph is representing C1, C2, C3, C1, C2, C3. Every graph is representing every different, classifiers, single classifiers. Okay. By the way, the distribution of these red dot and black dot. So let's say again, red dot means positive samples, and black dot means negative samples. Then we want to make very detailed and good classifier, but every single classifier looks like they don't generate any good results. They have some error. Okay, so to make a kind of very precise classifier, we can combine all these 3 classifiers, as you can see on the right bottom corner, the bigger graph. So by combining all these 3, then we can make a little bit more complicated, line. Then it means it can classify more in detail. Okay, more accurately. Okay, is that clear? So this is the concept of combination of classifiers. So one classifier, one simple classifier. So it means the rule is very simple. Oh, it is less than this value, one value, then phase. Larger than one value, this is non-phase. Actually, it is very simple and straightforward, but it is not so much accurate. But if we can combine multiple, rules, oh, this is larger than this value, but less than another value, for example. Okay, in that way, if we can combine multiple, threshold and multiple rules, then we can generate a better, more accurate, classifier, stronger classifier. Okay, so this is the concept of combination, and actually, this is becoming strong classifier. Okay, so by generating these single classifiers like C1, C2, C3 with good features, and then we can generate one strong classifier. Actually, this is the final target of AWS training system. Is that clear? Okay, so this is just a concept. Okay, so to achieve this goal, we need the next slide. Okay, let's go to the next slide. We need this kind of process. Okay, so we'll study step by step, about every stage to do this job. Okay, so this diagram is explaining the overall process of AWS algorithm. And in the beginning, we have one big set of training samples. Okay, it means positive and negative samples. So you can see at the top row of this diagram, so you have some face images and some non-face images, background images. Okay, so this is the training sample data set. Okay, and we also have a set of features, very large number of features, like over 180,000. Okay, so in this diagram, I just showed one example, FJ. So FJ is one of them. Okay, one of the 180,000 features, just for example, because it's too many to show, right? Okay, so the first step is to assign, weight to every sample, not feature. Okay, every sample. Here, every sample means every image, sample image, face or non-face, whatever. Okay, all the sample images have every corresponding weight, like W1. W1 is the weight for first sample. W2 is the weight for the second sample, blah, blah, blah. Okay? So every sample image is assigned to every weight. Okay? Yeah. So the first step is to normalize. We are initializing the weight, with the same value. Okay? And in training system, normally when we are dealing with weight, the sum of weight should be 1. Okay, that is kind of normalization to make the calculation easier. Okay, and normalized, right? So the normalization means, we are making the sum of all the weights equals to 1. That is the normalization. Okay, so that's the first step. So more important thing is, every sample has its corresponding weight, and in the beginning, they are starting with the same value. It's not random. Okay, not random. So sometimes some, training algorithms are starting like neural network, starting with some random value, but in this case, we are not, we are setting the same value and normalize the weight. Okay, and then we also prepare features from F1, Fj, and to F180,000. So we have a lot of features. Okay, they are ready here. Okay, so in the beginning part, we prepare samples with weight and features. So features are represented as symbol F. F means feature. Okay. So Owatara and as the question as probability. What do you mean? As 1 as probability? Yes, kind of, kind of probability. But it is not exactly probability. It is about weight. Okay. So weight is means normally the importance of the samples. Okay. Not exactly representing probability, but similar concept. Okay. Yeah. So here, one important thing you have to remember is, the index. Okay, because we have multiple dimensions. Okay, we have many samples. Normally, the number of samples is, tens of thousands. Okay, so tens of thousands, thousands of, base samples and thousands, more than, 10,000 of, the negative samples. Okay, so we have many sample images, and we have much more features, 180,000 features. Okay, so it is very big, different dimensions. Okay, so the index J in this, slide, index J is representing feature index. So Fj here, Fj means feature index J. So J can be 1, 2, 3, 4, blah blah blah. Okay. The last one can be 180,000, for example. Okay. Yeah. By the way, index I is representing the index of sample. So W1, W2, and Wn. The n is the maximum number of the last number of the sample. Okay. So, but when we are representing the every sample, we are using index I. For example, I want to represent, the third sample image. Then it can be xi. So here x variable is representing the sample. Okay. So first of all, you need to be familiar to this formula, to these symbols. Okay. If you don't understand about the symbols, then it can be very confusing to understand this algorithm. because we are dealing with multiple, not so many, but several, different, symbols. Okay. At first, it looks a little bit confusing. Okay. So again, F means features, W means weight, and F is using index J, and W is using index I, because W has the same, index with sample, because every W weight is corresponding to every sample. Okay, one sample, one W, one weight. Okay, sample is represented as symbol X. So X means one sample. So Xi, okay, Xi means the ith sample image. It can be third, 2, 3, 4, whatever. Okay, so X is also using index I, and W is using index I, and F is using index J. So here I and J are totally different index. Is it clear? Okay, yeah. So let's try to understand, the symbols now. But in the following pages, I have more detailed explanation. Okay. So for now, it may be a little bit, confusing because we have too many new symbols for now. Okay. And another symbol is E. Okay, so I will explain about H and Y a little bit later. Okay. One more symbol is E. Okay, here E means error. It's straightforward, right? Error, E. Okay. So from every feature, we can try to calculate the error. This is actually very beginning and very important step in this algorithm. Okay, so here you can see one strange looking formula like EJ equals sigma. Here the sigma means sum of W multiply HX minus Y. Looks a little bit strange, right? But yeah, we'll understand this concept soon. Okay. So anyways, E is calculated using this formula. So we'll discuss about this formula more in detail in the following pages. Okay. So one important thing here you have to understand is E is using index J. Okay. So what is J? Where is it from? Yes, exactly. Feature. Okay. So feature F is using index J. Okay. It means, every feature can have every error. Okay. Per one feature, we can calculate error EJ. For FJ, we can calculate error EJ using this formula. Okay. So E is corresponding, every E is corresponding to every single F feature. Sample is X. Okay. Sample is X. Here we, the term sample means, sample image. The face image, non-face image. Okay. So in this algorithm, the first step is to calculate this error EJ per every FJ. So it means for all 180,000 features, we have to calculate all 180,000 errors. Okay, it's a lot of number, but it is done by CPU, not yourself, so it's not a big deal. Okay, yeah. Anyway, so that is first step. E, we have to know the error of every feature. F. Okay, so that's why we are using the same index J. Okay, and then center left, is very curious about H and Y. Okay, so let's talk about Y. So we'll talk about this later more in detail, but Y means the label of every sample X. Okay, so Y is also using the same index I. Okay, the index of Y is I. Okay, so every sample, whether it is phase or non-phase, okay, so when it is phase, Y is 1. When it is non-phase, Y is 0. Okay, so this is kind of pair. So X and Y are pairs. Okay, so one sample image has one label. Oh, it is phase, then it will have Y value of 1. Okay, when it is non-phase, it will have Y value of 0. Okay, so X and Y are pairs. So Y represents the label. Okay, and age. Okay, so if you remember the concept of single classifier, in other words, weak classifier in the previous page. Okay, okay. Again, so let's make it sure. How can you make a single weak classifier from a feature? What do you have to add more? Yes, exactly. Threshold. I'm sorry, not coefficient. It's threshold. Okay, so we need to know the threshold. Okay, if we add threshold, do you remember the vertical and horizontal line in the graph? Okay, that is threshold. So if we know any threshold per feature, then we can classify. Yeah, the linear line. In this case, we are using very simple classification for weak classifier. So it is just linear classification, just linear line. Okay. So when we combine the threshold and feature, it is becoming one weak and simple single classifier. So it is represented with H. So H is corresponding to every feature, so it has index J. Okay, is it clear now? So H is we'll see the detailed formula, not formula but detailed logic for H, but later. Okay, so if let's look at this formula, our first formula again, EJ. So here, okay, EJ in the middle of the slide, right? On the right middle part of slide, you can see EJ equals, okay, sigma I, okay, sum of I, okay, WI. So W has index I, okay. So this sum is happening for W, every WI. So we are actually summing all the right formula per every sample actually. And then we are making the sum and it is becoming error. Okay, so WI is weight per every sample. HJ, okay, so this sum is working with index I. So HJ is not changing. So it means HJ is given with FJ fixed to calculate one error. And then WI, XI, YI are changing. So if you are implementing this in any kind of programming language, it will be a loop, okay, kind of for loop for all the samples. But here, HJ is not changing, fixed. Okay, so for the one given feature, FJ, we generate HJ, and then we calculate the error of EJ using this formula by calculating all the weights and this formula, and by adding all of them, we can generate error EJ. So this EJ will be the error of fj. Okay, and then once these errors, so every f will have its own error. So like E1, E2, E3, and E180,000. We have so many errors because per every feature. Okay. Then once we calculate all these errors, it may take some time, right? It is kind of iteration from number 1 to 180,000. Okay. So once we have all these numbers, then we will try to select the minimum one. So in terms of error, if we have minimum error, it means that is the best case, best feature. Okay, oh, it means, this feature, for example, f min, let's say min is number 200. It means, the feature 200 has the minimum error. So when error is small, it is better feature. Is that correct? So we will try to select the minimum E in this set of errors, big set of errors. And then the selected minimum one and the corresponding feature and H, weak classifier H, will be the selected best weak classifier, best feature at this step. Okay? And then the next step is to update the weight of every sample based on this selected, weak classifier. That is, again, in other words, selected feature. Okay. So, by the way, let's talk about the update, weight update later. It's too complicated, right? So now we have to understand, this error calculation more in detail. Okay, in the following page, we'll discuss more detail about this formula and this calculation. Okay. Any other question? Now, do you understand all the symbols? For now, I think it is enough to understand the symbols first. Is that clear? Any questions? No? Okay. Then let's go to the next step. Okay. Okay. So now to understand this algorithm, okay, first of all, the features are given in advance, right? We are assuming we have features. We are assuming we have samples, right? So let's think about features. Okay, for every feature, as we have already discussed, fj, we are using index j. Okay, for every single feature, we have too many features, but we have to process one by one. So for every feature, now to calculate the error, what we have to do is to make one weak classifier, weak simple single classifier of this feature. Okay, so per every classifier, we construct every weak classifier. Okay, for every feature. Okay, then how? Again, as we have already discussed, we need threshold. Okay, so this page is explaining, how it is not the full process, but what is the concept of threshold in this case. It is actually very straightforward. For example, okay, let's consider F1. This is highlight feature. If you look at the left side, over this face image, the girl's face image. Okay, I just displayed two sample features, F1, F2. So F1 is two rectangle highlight feature, vertical one. Okay, and F2 is three rectangle highlight feature, horizontal one. So these are just two from 180,000. Okay, just example for explanation. So in case of F1, okay, so for face image, I apply F1. Then F1 feature will return, the highlight feature value. It means one single value, scalar value of kind of subtraction using integral image, right? I believe you know the concept, right? So F1 will give us one value at this position of this face image, okay? Then in this example, just for understanding, I assume, the F1, showed this value 150 for this face image, okay? If you apply the same feature F1 to a non-face sample, like on the right side, okay, then the feature 1 value is becoming 300. Okay, so this is kind of example value. Okay. Then, okay, let's assume, we have just two samples, one face and one non-face. So face has, F1 value 150. Non-face has, F1 value of 300. Then for this feature 1, F1, what can be the threshold? The threshold can be in between 150 and 300. So, for example, we can say, 200 can be a threshold. Yes, exactly, yeah. So it means because it is in the middle between, 150 and 300. Okay, it can be something else, but just the example. Okay, if we set 200 as threshold, then from here, F1 can become a classifier. We can do some classification. We can say, we can make a kind of formula or code if the F1 value, when you apply F1 to any image, right? Any sample image. And if F1 value is less than 200, then you can classify the image as face. If F1 feature value for any image is larger than 200, then you can say it is non-face. Yes or no, right? So this is binary classification. Okay, so this is threshold. So this is the way we calculate the threshold. So when we apply the feature to all the images, sample images, and we try to find the median value between positive and negative samples. Okay, so in this case, we have just two, one face, one non-face, one positive, one negative. But when we have many positive and many negative, then we'll try to use the distribution value of, positive and negative samples in this feature space. Okay, yeah. So F2, in case of F2, another example, the face image, the positive one has a value 50. The negative one on the right side is the value 55. Then what can be the threshold? What threshold value do you want to use in this case? Yeah, exactly. In between 50 and 55. It can be 52, 53, 52.5, whatever. Okay, that's it. That is threshold. So once we calculate this kind of threshold per every feature, like F1, F2, F3, F4, F5, right? Blah, blah, blah. Then we can prepare the weak classifier H. Okay? So H is basically composed of feature and threshold. Simply saying. But later we will see the formal formula of H later. Okay? By the way, what is H? F means feature. Okay? E means error. W means weight. Why H? Why do we, so this is not so much important. We can use any other symbol, but in this case, why we are using symbol H for this simple binary classifier. Halt. Oh, you want to have a break? Reclassifier. Yes, exactly. It is reclassifier. We are using symbol H. Anybody has any kind of guess why it is H? We have many other symbols, right? It can be S, it can be T, it can be U, it can be V. Why just it is H? Why do you think the author is using H? Oh, heart-like feature. Yeah, well, it's a good guess. Good guess. But not sure, right? Okay, not sure. Okay. Feature classify in which is provides classify. Okay, let me answer the question a little bit later. Okay. Okay, so I'll give you a kind of very simple quiz to find out why it is H. Actually, you know, it is not selected randomly. Okay, it has some meaning. Okay, so I know the answer, so I will give you the answer later. Okay, so any time, you know, break time or whatever, you know, try to find out what it means. Actually, you know, it is not heart-like feature. Okay? It doesn't represent heart-like feature. Okay, yeah. So anyways, it is H. Okay, so I'll tell you the answer later. So to give you some chance to investigate by yourself. Okay. Okay. Or Watara. Okay. Answer. Ask the question. I would like to know feature are classified in each supervised classification. Okay, so the question is not so much clear, but if I am correct, okay. So it is like the relationship between the feature and supervised classification, okay. So in this process, as we have already discussed, we have feature, right? And by the way, we have positive and negative samples like this, the phase and non-phase. Then when we apply feature to positive and then negative samples in this way, we can analyze the values and then we can find the threshold in this way. Okay, so this is possible because we know which sample, which image is positive, which image is negative. Then we can select the threshold. If we don't know which one is positive, which one is negative, then it is impossible to calculate the threshold. Is that clear? So this feature and, you know, this the reclassifier can be generated because this is, you know, supervised classification, supervised learning in this case. Okay, let's go. Okay, so then, okay, so this slide is explaining, you know, how to apply every feature to every sample. So the previous one, we just assumed, you know, we have just two sample images, one positive, one negative, one phase, one non-phase. Okay, but in reality, we should use a lot of samples. Okay, it can be tens of thousands of, you know, samples. Okay, thousands of phase images and more than thousands of, you know, non-phase images. Normally, the non-phase, you know, negative sample has, you know, bigger size than positive samples. Okay, anyways, yeah. So instead of just two, we have to apply this FJ, every feature, to all the samples. Okay. By the way, we can have another feature, F2, for example. For F1, we have to do this. Okay. For F2, we have to do the same thing. So per every feature, we have to apply this feature to every sample. And the second feature, we have to apply to every sample. The third feature, we have to apply this for the sample. So it is kind of repetitive process. Okay, like for loop. Okay, so F is for loop, and samples another for loop. So this is in terms of programming, it is kind of a nested for loop of two for loops. Okay, the outer one is using index j, and the inner one is using index I. You should be careful about the index in that sense. Okay, yeah. So when I apply fj, for example, to every sample, like as you can see in this picture. Okay, so sample 1, x1. Okay, again, x means every sample image. X is image variable. Okay, you can see under every image, you can see x1, 1. Okay, x2, 1, x3, 1. Okay, oh, I'm sorry, x3, 0. Okay, so this is kind of pair. So x1 represents the image itself, and the number 1 is label. Number 0 is label. So the label is represented with symbol y. Okay, so at some point, for xn, it is paired with yn. It can be yn can be 0 or 1. It is kind of binary variable. Okay, so this is kind of just representation. Okay, and on top of that, every sample has w above, right? W1, W2, W3. So every sample has corresponding w value. So this is kind of number. Okay, the scalar number that is representing the weight per every sample. Okay, so if I apply fj to sample 1, x1, then it is fjx1. Then, for example, in this case, it has the value 150. If I apply the same feature to x2, the feature value is 130. x3, the feature value is 300. Okay, so in this way, we can generate the feature value, the scalar value per every sample for one feature. Okay, is it clear? So someone has a question. So we represent how good is the sample. Are we using the W, right? Yes, somehow, yeah. So W can represent that kind of information. Not directly, but it has that kind of meaning. Okay. But you have to remember it is not kind of directly. Okay, so for example, when W has a large value, you cannot just definitely say, oh, this is better. It is not so. That's not the purpose of this W. Okay, so W is kind of temporary variable to be used for the training process. Okay, so conceptually, it means how good is the sample, but it is not directly representing that kind of number. Okay, yeah. Okay, so this is the way, when we say, oh, we have to apply one feature to sample, then it is happening in this way. Okay, for every sample image, we generate the feature value. Okay. Yes, kind of relative, concept. Exactly. Not kind of, it cannot be a kind of absolute, value representing the, which one is good or bad kind of stuff. So we cannot compare that. Okay, it's just a relative, relationship. Okay, good, thank you. So is it clear now? So how to calculate, how to apply, feature to every sample, right? Then the result of this application, this calculation is feature value per every sample. Okay. So this page, the next one, is now representing the former formula for H. So now it's time to consider about H more in detail. Okay. So H here, in this case, H means the weak classifier of feature J. So H has index J. The J is number, right? But this index number is representing every feature. So one feature is corresponding to one H. Okay, that is Hj. By the way, Hj is a kind of function taking variable x. By the way, what is x? What does x mean? X means sample, exactly. X is sample, right? So image, okay? So we input image to this weak classifier H. Then this H, whatever it does internally, okay, it is returning binary results, 0 or 1. When H returns 1, it means H think the given image X is a face. Oh, I think it's a face. Okay. When H returns 0, it means H think whatever, whether it is correct or not. Okay. Think, oh, I think it is this X image is not a face, non-face. That is 0. Okay. So it is returning 1 or 0. 1 means yes, 0 means no. Kind of binary classification. Okay. So then internally, when can it say 1? Okay, so this is the core formula. Very simple. Actually, it is kind of simple binary thresholding. Okay, so F, here in this formula, the first line of this formula, in case of 1, okay, 1, Fjx. Again, here F is another function, the feature, okay, Fj, feature Fj. It is taking one image, X. What do you mean 1 point in image? 1 point? So we are not just, okay, yes, F is applied to one position, right? But actually it is a highlight feature, so it is taking the area, the region, the rectangle region. Okay, so as we have discussed, it is subtraction inside the region. Okay, anyway, so Fjx means, it is about from our previous slide. Okay, so it means we are applying feature J to image X. So X can be face or X can be non-face, whatever. Okay, then this F will return some value like 150, 200, 300, any number, feature value based on the highlight feature. Okay, so in this condition, if the left part Fjx will return some feature value. Okay, and then we compare this feature value with this theta, variable theta. Okay, theta is the symbol for threshold. So like our previous example, oh, the theta is 200. Okay, that is threshold value. So the feature value 150, for example, in this example, in the lower part of this slide, you can see the base image, and I applied one feature, highlight feature. This is Fj. Then its result, similar to our previous example, result 150. By the way, in this reclassifier H, theta, the threshold is 200. Oh, it is less than 200. So the result of hj for this image x1 equals 1. It is returning yes. 1 means yes. Is that correct? So this is the how this formula is applied for every single classification, weak classification, for every sample image. Okay. Our said image index. The image index is I. Okay. So in this formula, we are just assuming we have considering just one image x. So it doesn't have index for now. Okay. So your question is coefficient should be less than threshold, or what do you mean coefficient? Okay, so as for P, okay, we haven't discussed about P, right? So let's discuss about it after this question, okay? Coefficient, what do you mean? Okay. Okay, so another question. Okay, feature coefficient Fj. Okay, yeah. So okay. So coefficient is not the kind of proper, word. Okay. So feature value Fj, it is value, right? Like 150. Okay. But sometimes it can be less than threshold theta. Okay. Sometimes it can be larger than theta threshold. Okay. So to be a phase, it should be less than threshold. Okay. According to the weak classifier. But it's not always true because the weak classifier is not 100% perfect. So it is not what it is saying. Oh, I think it is phase, but we cannot believe it 100%. That's why we want to calculate the error of every weak classifier. Is it clear? Okay, yeah, okay. Okay, so another question, H and Y. Okay, so it looks like, the result of H looks very similar to Y, right? That's why I think, you are asking this question. I think, Rawa asked the question, right? H and Y. What's the relationship? That's very important and good question. Okay. So then what is Y and what is H? Okay. What's the relationship? So Y means, the input label. So again, you have to remind, it is supervised learning. Okay. So we are assuming we definitely, absolutely exactly know the label. Why? Okay. Oh, this is phase. This is non-phase. It is given in advance from kind of God. Okay. It's very, we are assuming it is true. Always true. Okay. By the way, when I apply the feature, this Fj, and when I calculated, Hj, and it returns some similar value, 0, similar to Y, right? 0 or 1. Okay. By the way, this result of H reclassifier is not always same as Y. By the way, let's consider this example. Oh, this is phase image, definitely, right? This is 100% phase. Okay. So the Y value of this X, image X, will be 1 in the database. Okay. By the way, when I applied like, oh, this Fj returned a good result. Okay. Oh, it is phase 1. Okay. By the way, let's get another case like when I applied feature 1000. Okay. Feature number 1000. That feature was not so good. So it returned 0, whatever reason. Oh, by the way, Y is 1. That feature H1000 from feature 1000 is returning 0. It means it failed to classify this image. Okay. So for certain image and for certain feature, sometimes they can fail. There is no feature, 100% perfect with this kind of weak features. Okay. So y is kind of the base number. Okay. Yeah. And h is a result of every weak classifier, but we cannot believe them all. Okay. So step, mathematically, very simple one. So if you look at this slide, it is saying Pj. Okay, Pj. Okay. Oh, Tara, you said error equals 0, then y equals h. Yes, exactly. Yeah. Thank you. So Pj here, you have to be careful. P is using index j. Okay. So every feature, every exactly saying, every reclassifier hj, okay, it has pj. So by the way, the role of pj, it doesn't have any serious meaning. Okay. So pj is indicating the direction of the inequality sign. So based on very elementary level math. Okay. So when we have the inequality sign, the pj can have value of positive 1 or negative 1. Positive 1 or negative 1. Okay. So what someone answered is some feature bigger is better, sometimes not, and that representing. Yes, exactly. Okay. So sometimes we have to say, oh, f should be less than theta threshold. By the way, sometimes some different features, the direction of this inequality sign should be opposite. Oh, f should be larger than theta. Then we can give p negative 1 instead of positive 1. In general, when f should be less than threshold, then p is positive 1 in that case. So if when we are analyzing, the feature space and try to select threshold, then we also can recognize the direction. Oh, which side is space? The less than is space or larger than is space? Is that correct? So we can determine P. So this is the basic formula. F is less than threshold, theta. This is the base. But if it is not in this case, f should be larger than threshold to be a phase, then we can give p negative 1. Okay, so p is positive 1 or negative 1. Is it clear? Okay, so p doesn't include any serious, kind of number or meaning, just, the direction, changing the direction. So some h can have negative 1 of p, but some h can have positive 1. So p is using index j. It is per every weak classifier. Okay. Is it clear now? So this is weak classifier h. Okay. And so p is just kind of, very simple direction. So basically, weak classifier h is composed of feature fj and threshold theta j. Okay, so this is weak classifier. Any question? Good. Okay. Yeah. I think the next step is how to calculate the error. What is the concept of error? Okay. So I think we'd better have a break first before we go to the next serious topic. Okay. So the calculation of error is very important part of this AWS algorithm. So we have to discuss more in detail about this process of error calculation. Okay. So then let's have a break, 10 minutes. This is 39. So until 37. So until 47. Okay. So now using this reclassifier. Okay. So by the way, every reclassifier in this way, as we have already discussed, it can give us the right answer. So how can you know if the classifier is giving us the correct answer or wrong answer? How can we know that? Actually, it is already, something we have already discussed. It is about symbol. Which one? Yeah, the result is determined by threshold, right? It's depending on threshold, right? So after the thresholding, and it gives us a result. It can be 1, sometimes 0, right? By the way, again, it is hypothesis. It is not absolute answer, not always correct answer. Sometimes it is correct, sometimes it is wrong. You understand, right? So every reclassifier can give us wrong answer. Is that correct? Then systematically, okay, how can we calculate or how can we know if it is wrong or correct? How can you know? We already have that information. Yes, exactly. Y. Okay, you answered about H and Y, right? So H and Y are not always the same because the classifiers cannot be always, correct. Okay, so in practice, there is no reclassifier. It is 100% correct. So sometimes it is wrong. It means the result of H and result of Y can be different. So from this difference, we can calculate the error. Okay. For example, if we compare two reclassifier, H1, H2, H1 gives us 3 wrong answers. H2 gives us 10 wrong answers based on Y. Okay. Then which one is better? H1 or H2? Yeah, H1. Very straightforward, right? Right? So this error, so this failure, wrong answers are considered as error. When anyone, any H, any reclassifier H has bigger error, it is bad one. Any H has smaller error, then it is better reclassifier. Okay, so that is the purpose of calculation of this error. So from now, we are going to see how we can calculate the error. Okay, that is the concept. So this picture, this slide is showing the process of applying every fj. So it is about the every reclassifier. Okay, so it is same as hj. Okay, so whenever now from now when we say a fj, then it means it is same as, almost same as, Hj. They are all connected. Okay. So when I apply the Fj to all the samples, then this, in the lower part of this this slide, you can see one graph. Okay. So this graph, x-axis means every sample, x, just x. Okay. This y-axis, vertical axis, not y, but it means f, fx. So every given sample, we can calculate feature value. So this white line, okay, white graph, is representing the distribution of f value. Not exactly, probabilistic, distribution, just, plotting the f value. Okay. By the way, this yellow vertical line is representing the phase and non-phase. Okay, the left part of this left is phase, the right part is non-phase, positive and negative. Okay, so when we have these values, as we have already discussed, then we can determine the threshold by using some median value or average value. Okay, let's go to the next step. Next page. Okay, so based on this current graph, okay, then on the vertical axis, we can draw one green, this kind of green line. This is threshold, theta, okay. So because the vertical axis is representing the feature values, right? So we can set one threshold, theta, this green line. Okay. Then we know which sample is positive. The left part is positive and right part is negative. Okay. So if this feature and this reclassifier Hj is perfect, then what should happen? The white line on the left side of yellow should be all below green. Okay. And the white line on the right side of this yellow line, all above green. Okay. Then it is perfect, 100%, perfect, reclassifier. But in reality, we don't have that kind of graph. Okay. So this is the example. This is kind of a little bit more realistic graph, right? Oh, ideally, we should not have any value higher than this green threshold on the left side. Okay, but I'm sorry. So this the direction is opposite. Okay, so in this case, the direction is, f is larger than threshold. Okay, so ideally, on the left side, all the white ones should be larger than this green. Okay. On the right side, all the white, graph should be below, less than the green line. That is the ideal case. Okay. But if you look at on the left side of the yellow line, some parts of this colored area, okay, like this one and this one, some part of the graph is below green line. It means they are saying wrong answer. Okay, they will say what would be the answer of reclassify H in this case. It is. So they should be 1, right? Because they are all faces. The left part of this yellow vertical line, all face, right? They're all face. But for this, colored area, it is below green. It means H will say, oh, this is 0. we are talking about the left part, not right one. Okay. So you can see the orange colored hatched area. Okay, that is the error case because faces should be larger than green line. Okay, the threshold. That is H, current H. We are now talking about just one H, right? One weak classifier. Okay, but this area again, this orange hatched area, colored area, they are below green line, even though they should be above. Then it means H is giving us 0 for these samples. Okay, so this number of samples are becoming error. Yes. Okay. Now let's consider the right side. The right side of this yellow vertical line means negative samples. Okay. Then ideally the H, the result of reclassifier, should be all 0. But for this large area of hatched orange colored line, area, it is saying 1 because they are above green line. So this is wrong answer. So this is another error. Okay. So the left part, the errors, when it should be 1, it is giving us 0. It means, when based on Y, okay, Y value, we know Y, but the label, okay. When it should be 1, it should be face. This H reclassifier is saying no, 0 for certain, samples. So this is false negative. False negative. Do you remember the concept of false negative? Okay, so there's one question from Watara. So in that case, can we take the absolute value of F? No. So F should not be absolute. It can be negative sometimes. So this is just, subtraction. Okay? Yeah. Okay. So false negative. So it means, the classifier H returns 0 because this is below green line in this case, right? But this is negative result, negative. So the classifier is saying negative. But this decision is wrong. So this is false negative. Okay. On the right side, for this area, the wrong answer, error case, okay, then it is called false positive. It means, when the answer should be 0 because this is non-face area. But these guys are saying, are having results of 1. It is saying, oh, this face. The H, this reclassifier is saying, oh, these samples are faces. It's wrong. So false positive. The classifier is saying positive, or this is face, but this answer is wrong. So this is false positive. Okay. So finally, errors are calculated using this, false negative and false positive area. Okay. So that is this formula, EJ. So now we have to understand this formula. So EJ is calculated as sum of all I. Okay, so this I means all the samples, right? Sum of all the samples, index I. It means the x-axis in this graph. So for every sample image, I, okay, then the first term we are multiplying is WI. Okay, WI. Okay, W was the weight. Okay, weight. Okay, so we just weight, multiply weight. So weight is per every sample. Every sample has its own weight. So we are multiplying weight. So we'll discuss about the weight later. Okay, Anyway, we have some weight. Multiply. And then the next term is absolute value. You know what is absolute, right? Absolute, this, vertical bar mathematically means absolute, right? The negative is becoming positive. The absolute value of subtraction between h and y, simply saying. So h, j, x, I believe now you can understand what it means, right? So that is the result of the given weak classifier hj. Okay, so now we are calculating this error for one weak classifier, j. J is fixed. Okay, so we know we have the weak classifier hj. Okay, so hjxi means for every xi, sample I, okay, when I input that image to this weak classifier hj, what can be the result of this hjxi? The result can be sometimes 1, sometimes 0. Yes, exactly. Is that clear? Okay. When this hj say 1, okay, it means the weak classifier thinks the input image xi is a face. When hj say 0, it means, oh, I think it is a non-face. Again, this answer is not perfect. Can be 0 sometimes, can be correct, sometimes can be wrong. Okay. Yes, I think you understood already. Yes, exactly. So when the answer of hj is correct, it means it will give us the same answer as y. Okay, we already, again, so we know y, okay, the label. So let's say it is face image, xi was face, then y will be 1. Okay, by the way, h returned 1. Oh, it is saying face. Oh, I think it's face. Then this answer is correct. Then 1 minus 1 becomes 0. Then 0 is multiplied to weight. Then nothing is added to the error. Is that correct? Okay, so the other case, when, again, in the same way, current xi is face, then yi will be 1. By the way, this we classify h say 0. Oh, it is not a face. It means false negative, error. Okay? Then h is 0. Then 0 minus 1, because it was error. Then this absolute value will be 1. Then the wi will be accumulated to this error. Is that clear? So if this weak classifier hj returns many wrong answers, then it will accumulate many weights. Then error is becoming bigger. Okay? If hj is much better, another hj is much better, then it is giving us a small number of wrong answers. Then we just add small number of weights. Then the number e will be smaller. Is that clear? So in this way, we can calculate the error. Okay, so the error is the weighted sum of value. More exactly saying, the weighted sum of false negative and false positive. So when I say weighted, it means weight is multiplied to every error. Is that clear? Okay, so this is how we calculate error EJ. So to calculate the error EJ of every weak classifier HJ, then we have to iterate all the samples. We have to calculate the feature for all the samples. Then we can accumulate the error weight. Then we can have E, J. So every reclassifier H, how many do you have? 180,000, so many, okay? So whatever many, it is just kind of one for loop in terms of programming, right? So for all the reclassifiers, 180,000, we calculate error E1, E2, E3 until E180,000. That is the error calculation. Okay, so this is very important step. Okay, so the next slide is actually explaining this process a little bit more in detail, right? So when H is 0, Y equals 1, the absolute value of H minus Y equals 1. So when H is 1, Y2 is 1, then the absolute value is 0. So correct case, it is not accumulating the weight. Okay, I think you have understood this concept already. Anybody has any question about this process? So this is very important step. Okay, so it is important to understand this one. Okay, so now we can calculate the errors of all the features. In other words, for all the reclassifier. So in this slide number 26, we can formulate all the symbols. So for H1, reclassifier H1, it has its corresponding feature F1 and theta 1, error E1. Okay, so until now we calculated all these three values, symbols, right? So we know how to define the F feature, how to define H, reclassifier. We know how to calculate theta, and we know how to calculate error E. Okay, so that is our current status. Okay, and in the future, after some more processing, we will see one more symbol, alpha. Alpha. Okay, so alpha is also assigned to every reclassifier. Okay, let's talk about alpha. We haven't discussed about alpha yet. Okay, let's talk about alpha later. Okay, and again, every sample has corresponding weight W. Okay, as we have already discussed, W is not generating any serious output. So this is kind of temporary weight just to calculate error. Okay, but during the kind of just training process, so we are not producing any output with W. So this is just internal usage. Okay. Yeah. Okay. That's it. For our sample, all W are the same weight. Oh, okay. No. Actually, we are starting in the beginning. We haven't discussed about that process yet. Okay, we'll see the detailed process later. In the beginning, we are starting with the sample weight. I'm sorry, the same weight. We are assigning all the same weight. We are normalizing in the same way. So we are starting with all same weight. But the next step of error calculation is weight updating. We haven't studied it yet. We'll discuss soon. Okay. So in the process of weight update, every weight will be updated in some different way. So the weight can be changed for some samples, not all the samples in the same way. So finally, they will have different weight as we continue the training process, iteration. Okay. Wait a minute. let me. Okay, let's go. Okay, so next page. Okay, 27. So in this diagram, so this is showing the details. So until now, we have discussed about the error calculation step, right? So this is a very detailed every step of this algorithm. So here we can see how we can initialize weight and how we can update weight. Okay, okay. Let's talk about this step. Step. So first step, we are giving example images. So here is the example means sample images, x, comma, y. So now I believe you understand what is x and y, what is y. Okay. And in the step 2, we assign for every sample image, we assign wi. Okay. By the way, the wi is assigned in the beginning with actually the same number, 1 over 2m and 1 over 2l. Okay, here m and l means negative and positive numbers, number of negative and positive samples. So in this way, we can give same weight for all the negative samples divided by 2m. So m is number of all the negative samples. And for the positive samples, for face images, we give the number of 1 over 2l. So in this way, the 2 means, we have two different parts, right? Positive and negative. So that, all the sum can be, 1. Okay, yeah, exactly. But, the positive samples will have the same weight. Negative samples will have same weight. But positive and negative weight may not be the same. Sometimes it can be same if we are using the same size of positive and negative. But in practice, we are giving much more negative samples. Okay, if you give same number of negative samples as the positive one, then you may not expect any good results. Normally, we are giving much bigger negative samples. So in that sense, the rates of negative and positive will be different. Which one is bigger? Positive samples will have bigger weight. Okay, great. Okay, so this is the starting. Okay, so we have, but so simply saying, we can say, oh, they have all the same weight. Okay, not exactly, but simply saying. Okay, they don't have any different values, not random. Okay, okay. Then now we are normalizing the weight. So in the beginning, it was already normalized, but this process is kind of iteration. Okay, so every iteration, because the update can be changed from previous step, previous iteration. So we have to normalize the weight first. Okay, so this is kind of inside the loop. And then for every feature j, fj, okay, we train a classifier hj. Okay, so it means we are calculating the features and errors. Okay, and at this step, second step, we select the weak classifier. So it means, we select the best weak classifier. So how many classifiers do we have? 180,000, so many. By the way, after calculating the error using this formula, E equals, sigma WH minus Y, okay? So we can calculate the error of all the weak classifier at this step based on the given initial weight. Okay, so now you can understand, the error value is depending on W. It is also depending on the H minus Y, right? But it is also depending on W. Yes, exactly. So after calculating all the error, we can sort the reclassifiers based on the error. Then we can select the best one. The best one means that one reclassifier that has the minimum error. That is, the best reclassifier at this moment. Okay, that's the error. Okay, that is the best reclassifier. Is it clear? And then the next step, number 3, is update the weight. Update the weight. So this one, this concept is a little bit tricky in the beginning to understand. Okay. So based on the select, okay, so among those many, reclassifiers, we selected one winner. Okay, one winner. So one best reclassifier. Then from this classifier's point of view, even though this selected classifier H something, HT, we call it as T because this is iteration for loop. So first we selected classifier H1, okay? Then it is not perfect, not 100%, but anyways, it's the best one, okay? Then we can consider every sample based on the point of view of this selected best reclassifier. So this reclassifier can determine, okay, from my point of view, which sample is good, which sample is bad. So that concept is, applied by updating the weight. So update process. So because again, as we have already discussed in the beginning, the weight can represent, how good every sample is. So sometimes even though we have two different, face images, but some face images can be good. Some face image can be blurred or not good. Okay, but they may have some different, quality, especially from the classifier's point of view. Okay, so this face is easy to classify from my current classifier, or the other one is very hard to classify, right? So that is kind of the update. Okay, so the selected reclassifier is trying to update the weight based on its point of view. When the classifier thinks every image is sample image is good to classify it. Okay, it means simply saying, when it is it can be classified by myself, my current classifier, well, then they are good. When it fails, then it is bad. Okay, the weight is bad. Okay, so in the way we are updating the weight. So this green box, number 1, 2, 3 steps. Normalize weight. After once it is updated, then it should be normalized again. The update is not guaranteeing the sum of the weight to 1. Okay, so we have normalized, and then we calculate the error again in number 2 step, and select the best one again, and then update the weight again. This is loop, for loop. Okay, so we are using, in this case, we are using index t. Okay, so if I do one loop, that is t is 1. If I do one more, t is second 2. Okay, if I do one more, t is becoming 3. In this way, we are looping this loop until large t. So this large t, simply saying the number of this iteration is given by the engineer. Okay, so it depends on how many reclassifiers do you want to select. So basically, this loop is actually selecting good reclassifiers. So in the first loop, we select 1. By the way, every loop, how can we select different, weak classifiers in every loop. Basically, if one weak classifier is good, best, then it should be always selected, right? Is that correct? Well, then we don't need to loop so many times, 2000 kind of times. Large T can be 2000, for example. Okay. We have to remove it once it's selected, right? That's your answer. It can be one. It means, you want to select the best one first and remove it. You want to select the second one, the other one, blah, 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 right? That's your approach. Okay. But in this diagram, there is no such step, right? Yes, exactly. So the way this algorithm is doing is updating the weight. Okay, so if you remind the process of error calculation, it is depending on weight, W. Okay, if we update the W in previous iteration, then in the next iteration, the error value can change. Okay, then it can change the selection because error has been changed, right? So the best weak classifier can be changed or may not be changed. We don't know yet, right? But normally it can change. So for example, in the first iteration, we selected H500 as the winner. Oh, you are the best one. By the way, after updating the weight, if you do the same process again, even though it is the same formula, but W's are different. So, for example, H200 can be selected as the best one with minimum error. Is that clear? So in this way, we are iterating again and again and again. So in every loop, we are updating the weight. Okay, so as you can see in this, diagram, step 3, update the weight is inside the green box, right? It means it is inside the for loop. So in every loop, we calculate the error, select the best one, and based on the best one, we update the weight. And then the next loop, calculate error, select the best one, and update the weight. So in this way, in every iteration of T, we expect to have some different, weak classifiers, some good weak classifiers, not the best, just the best one. So in this way, we set the large T, as like, normally 2000. So we collect 2000 good weak classifier out of 180,000. No. So it doesn't mean, the last one is the strongest. We cannot guarantee that. Okay. So this update process, it is just trying to change the, the weight, and it is, we'll discuss about the weight update process later. Okay, not today. But it is actually simply saying it can give us another point of view, and it can give us, other chance to select different, reclassifier as a next reclassifier. Okay, so let's discuss about that concept later more in detail. Okay, so one question is, Otara asks a question, does it take too much time for system to browse the best classifier? Too much time. Actually, this process, I don't understand the concept of browse. Yeah, browse the best classifier. But anyways, as for this loop, okay, so you are correct. it takes a long time. Okay. So this kind of AdaBoost and, cascade, even we have the next step, we have a cascaded AdaBoost, right? So this cascaded AdaBoost takes very relatively longer time than other machine learning algorithms. So for example, for like face detection, it may take many hours, sometimes days. Okay, yeah. Oh, someone's question is that done offline? What do you mean offline in this case? Bentalab asked, oh, how can we update the weight? Okay, that is the next step. Okay, so we discuss about the details. It is a very kind of important concept. Okay, so we discuss about it later. The next lesson. One time when training the system. Okay, yeah. So this training is happening just one time, right? So when we are detecting face, we don't do this step again. Okay. Once it is done, then we just use the trained data. So we are not training every time. Okay. So it is impossible. Yes, sure, yes. Once it is trained, right? Training is finished. Then the object detection is just using the result of this training. Okay, it is not training again and again and again. Okay, I think that is the concept of offline you step, right? Is it clear now? Okay, excellent. Okay, so I think that is all for today. So as for the weight update, there are some more formula and some more concepts. Okay, so I think we can discuss more in depth next week, next class. Okay. By the way, I heard from Elham, yeah, you have a holiday in Paris, France, next week, right? Next Friday. So you don't have class next Friday. Is that clear? So we move the class to December. Okay. So we have one class next Thursday morning. Okay, as usual. Okay. Okay. So let's remember. Okay. Now let's focus on this error. Okay, how error is calculated, and how the best one is selected. Okay, and error update. No, next week. Okay. Any last question? Everything good? Clear? Okay. Okay, guys. Thank you very much, and have a nice weekend. And see you next week. Thank you.